Google has introduced a quantum computing chip that transforms what we know about computation. After years of breakthroughs, Willow brings precision and scalability that redefine the possibilities for quantum systems and AI. The chip tackles one of the toughest challenges in quantum computing by reducing errors as the system scales. With every additional qubit, Willow enhances stability, demonstrating the kind of reliability needed for large-scale systems. This advancement sets the stage for entirely new ways of solving complex problems. And of course, this chip changes everything for AI. It boosts training speeds, handles enormous amounts of data with ease, and gives AI the ability to tackle problems that were out of reach until now. The combination of quantum computing and AI is opening new possibilities that feel limitless. Google has created something that takes AI and innovation to a completely new level, and the future is looking more powerful than ever. So how far can AI go when powered by quantum computing, and what happens when machines surpass limits we never imagined? Are we looking at a future full of breakthroughs, or something we're not ready to control? Let's explore what this means and uncover where it's all heading. All right, so quantum computing has always been about harnessing the strange and powerful principles of quantum mechanics to tackle problems that classical computers just can't manage. Regular computers operate with bits that are either a 0 or a 1. Quantum computers use qubits, which can be 0, 1, or both at the same time, due to a property called superposition. This, combined with quantum entanglement, where qubits are linked in such a way that the state of one affects another no matter the distance, allows quantum computers to process information in a way that's fundamentally different and vastly more powerful. But for all their promise, quantum systems have faced a daunting obstacle: errors. Qubits are notoriously unstable. They interact with their environment, losing the information they're supposed to maintain. The more qubits in the system, the higher the chance of errors, making large-scale quantum computing incredibly difficult to achieve. That's where Willow changes everything. Willow is a breakthrough in overcoming this challenge. It's the first quantum chip to demonstrate below-threshold error rates, meaning that as more qubits are added to the system, errors don't increase uncontrollably. Instead, they decrease exponentially. This accomplishment wasn't achieved overnight. Researchers scaled up arrays of qubits, first using a 3x3 grid, then 5x5, and finally 7x7. And with each increase, Willow cut error rates in half. This exponential reduction in errors proves that quantum error correction works on a large scale, something scientists have pursued since the concept was first proposed by Peter Shor in 1995. This isn't just theoretical progress. Willow has also demonstrated real-time error correction, a crucial requirement for any practical quantum computation. Without correcting errors as they happen, quantum systems lose coherence too quickly to complete meaningful tasks. Willow's ability to extend the lifetime of qubit arrays beyond the lifetime of individual qubits is a clear sign that error correction is improving the system as a whole. It's the most convincing prototype of a scalable logical qubit ever built, and it's a major step towards a future where quantum computers can handle problems that classical computers will never be able to solve. Performance-wise, Willow has set a new benchmark in the field. Google used the Random Circuit Sampling (RCS) test, a challenging computation that checks whether a quantum system can outperform a classical one. Willow completed the task in under 5 minutes, a feat that would take today's fastest classical supercomputers, like Frontier, 10 septillion years. That's 10 followed by 24 zeros, or more time than the age of the universe. These numbers underscore just how far quantum computing has come, and they're a testament to the staggering potential of this technology. Google's conservative estimates for these computations factored in ideal conditions for the classical systems, yet Willow still outpaced them by an astronomical margin. This achievement puts the chip in a league of its own, demonstrating a performance gap between classical and quantum systems that continues to grow at a double exponential rate. There's more to this story than raw speed. Hartmut Neven, the founder of Google Quantum AI, highlighted something that's both fascinating and controversial. He suggested that Willow's unprecedented performance might be explained by quantum computation happening across multiple parallel universes. While this concept, rooted in the multiverse theory proposed by David Deutsch, is still speculative, it's a mind-bending way to think about the potential of quantum mechanics. Even if the multiverse interpretation remains unproven, the sheer capabilities of Willow offer a glimpse into a computational future that defies traditional limits. It's not just about theoretical milestones, though. Willow's success has immediate implications for how we think about making quantum systems commercially viable. Today, quantum computing experiments fall into two categories: performance benchmarks like RCS, which lack direct real-world applications, and simulations of quantum systems that, while scientifically valuable, are still within the reach of classical computers. The next big goal is to combine these strengths by running computations that are not only beyond the capabilities of classical systems, but also useful for solving real-world problems. This is where the potential for quantum computing really shines. Applications in fields like medicine, energy, and materials science could revolutionize entire industries. For instance, quantum systems could help design new drugs, create better batteries, and even accelerate breakthroughs in fusion energy. These are problems that classical computers struggle with, but quantum systems could handle them with ease. Building Willow wasn't just about throwing more qubits into the mix. The chip was developed in Google's state-of-the-art fabrication facility in Santa Barbara, one of only a few such facilities in the world. Every aspect of the chip's design, from its architecture to its gates and readout mechanisms, had to be optimized to work together seamlessly. The quality of each component matters as much as the quantity. Willow's qubits have a tone time, the time they can maintain quantum information, of nearly 100 microseconds, a 5-fold improvement over previous generations. This focus on quality over sheer numbers ensures that the system can achieve reliable performance at scale. The implications of Willow's development extend far beyond quantum computing itself. Quantum technology is poised to enhance advancements in AI, creating a powerful synergy between two of the most transformative technologies of our time. Quantum systems could help train AI models more efficiently, optimize complex algorithms, and analyze data that's currently inaccessible. This partnership between AI and quantum computing could lead to faster progress in fields ranging from scientific research to practical applications like autonomous vehicles and renewable energy. The impact of Willow's announcement was immediate. Alphabet's stock surged by 5% following the reveal, as investors recognized the potential of this breakthrough, with competitors like Microsoft and Quantinuum also pushing the boundaries of quantum technology. The race to achieve commercially viable quantum systems is heating up. But Willow's achievements set a new standard, demonstrating that error correction and scalable systems are no longer just theoretical goals, but achievable realities. Despite its accomplishments, there's still a long way to go. The challenge now is to bridge the gap between experimental demonstrations and practical applications. Google's roadmap for quantum computing includes milestones like achieving a useful, beyond classical, computation obstera, and computation obstera, one that solves a real-world problem more effectively than any classical system. To get there, Google is inviting researchers and developers to collaborate by exploring their open-source tools and educational resources, including a new course on quantum error correction available on Coursera. The hope is that a broader community effort will accelerate the development of algorithms capable of tackling the challenges of the future. This breakthrough marks a turning point in the progress of quantum computing. It's more than a milestone, it's a clear signal of how this technology could transform the way we solve problems and innovate. From advancing AI to tackling some of the hardest challenges in science and industry, quantum computing is set to drive major change. This achievement shows that the future we've been working toward is closer than ever.